Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing sediment data, specifically boundary conditions. So where that is in HEC RAS here on the screen, I've got my HEC RAS user interface with the files and the geometric data editor. If we're editing sediment data, go ahead and click on this sediment button right here, or you can go to edit sediment data. And then for this lesson, we're going to be talking about this second tab right here for boundary conditions. What we talked about in the previous lesson, lesson 53, that was this first tab, initial conditions and transport parameters. Go ahead and check that out if you want. But what we're going to be covering here is now boundary conditions. Also, file management tools are available here in the file manager. So you can create a new sediment data, open, save, rename, and delete. All right, I'm currently working on a test 3. That's the name of this sediment file. So I can create a new sediment file if I want. Let's just do that. Okay, don't need to save that. I'll just call this test 4 so we can get started off with a fresh new sediment file. And then it does open me up to this first tab by default, but we're going to click on boundary conditions. So these first two tabs are required, both the initial conditions and the boundary conditions. I'm going to move this over to the side here just so we can get a look at the model. We have a river A, which starts at river station 5000 and it flows all the way down to river station 0 here. That's the main river. And then at this junction 1, we have river B that splits off to the left. HEC RAS requires sediment data at each upstream model boundary and can also include optional local lateral sediment loads where necessary. So that's why right here in this table, I have the one and only upstream river station location. This first column is river and then reach and then river station. I think it's supposed to be labeled up here, but I don't see it right now. And that's what it is starting me off as a default. So I need to define something here for river station 5000. However, I can also add boundary conditions at other locations. So if I wanted to add a new row here representing a new boundary location, I can go ahead and click add sediment boundary locations. And then I can specify the river, I can specify the reach, and then the river station. So if I select 3000 and then the arrow, okay, I already had it over here. Boom, and then click OK. That adds a new row in my table, which represents a new boundary location. And I'm not sure what this is. In addition to river cross sections, I can also add a junction. To do that, click this button for define sediment split at a junction. I only have one junction in my model, so that's called junction 1, and then click OK. All right, so this is my row for the junction. So this row right here represents the boundary location at junction 1. All right, so as you may have noticed, as I highlight and click on each of these different boundary locations, different boundary condition buttons become enabled and disabled. So for instance, at the top of the reach, this top row of buttons are all available for me. And then downstream at an intermediate cross-section 3000, the only available boundary condition is this sediment load series. However, if this cross-section 3000 has a lateral flow associated with it, I believe that's defined in the unsteady flow data, then I would have additional options available. So let's go ahead and do that. I'm going to click on River Station 3000 and then go up to my unsteady flow editor. Here is the dialog box for unsteady flow. What I'm going to do here is click on add a river station and then river A, reach 1. This is going to be for river station 3000, that cross section right there. Click OK. And then if I click on that road right there, I can just add, for instance, lateral inflow hydrograph, uniform lateral inflow hydrograph, or some of these other options. Let's just go ahead and use lateral inflow hydrograph. I'm going to switch the time interval to something a lot larger, like 1 day. And then I'll just define a constant inflow of 500 CFS. Okay, I'm going to go ahead and file, save. I'll just call that test 4 as well. I don't know if I need to do all that, but let's go back to our sediment data. Here's the boundary condition. All right, so I clicked off of that row and then back on just to kind of refresh the interface. And now HEC RAS realizes that associated with that river station 3000, there is inflow. And now I have these additional buttons available. These are all different boundary condition options available for my cross section at an intermediate location. And then the junction options are this bottom row right here. So let's go ahead and just start talking about these different buttons and the data required for that particular boundary condition. So I'm just going to first define River Station 5000 at the top of the reach and click on Rating Curve. A rating curve computes sediment boundary loads based on boundary flows. This is also available for upstream boundary conditions, but only available for internal boundary conditions if if there's cross-section data that we added, like for River Station 3000. Okay, the first row of this table is the flow rate in CFS. So what we'd go ahead and do is specify a flow rate, maybe something like 100 CFS and 1000 CFS. The range of flow rates in these columns here should completely subsume the range of flow rates that will be used in the simulation. If I want to add or remove columns from this table, I go ahead and do that from this drop down here. By default, it starts me off at 2, but I can obviously add more. I'm just going to keep it at 2 though. This is called the number of flow load points because what we're doing here is defining the sediment load for that particular flow rate. So my range of flows is 100 CFS to 1000 CFS. And say, for instance, my simulation was a minimum of 200 CFS up to 500 CFS, then this range of flows would be appropriate. However, if the flow from the simulation, for instance, exceeds the maximum value defined here in the column with the highest flow, then the HEC RAS would just assign these numbers of the highest flow to whatever flow rate was above that maximum. The next row down here is total load, and that's in tons per day. This is mass per time, which is associated with the radio button that's selected by default at the bottom here for load. The other option is concentration. So if I click on concentration, this is mass per volume. And even though my model is US customary units, it does use metric concentration regardless in milligrams per liter here. And same is true with the sieve sizes. It's always in millimeters, even if your model is using US customary units. So I'm going to change this back to load, and then I'm going to start typing in some numbers here. So total load, I'll say 5 tons per day at 100 CFS or 500 tons per day at 1000 CFS. And then below that, I need to specify the actual load in each of these different grain size classes. So clay, for instance, is 0.002 millimeters to 0.004 millimeters. So I'm going to start typing in some numbers here. All right, I've added some numbers here for both 100 CFS and 1000 CFS. If these values do not sum up to 100%, that's fine. It will, HEC RAS will normalize that data. These values here are not percent finer, which you may be familiar with on grain size distribution. This is basically a percentage of the overall fraction based on that particle size class. I forgot to mention that this total load can be converted by clicking on the concentration to load button back and forth here. Now, if I want to preserve the same value and it's 5 and 500, I'll just click on the concentration button and the label changes. But if I'm in load and I want to change it to concentration and make that conversion, click the button here, and then that will convert the values accordingly. Okay, and then if I can convert it back, just the same. Also, there's a plot button here. This only refers to the flow versus the total load, not the actual particle size distribution. So if I click plot, I only have 2 data points, so that's why this looks like a straight line with a minimum flow of 100 and a maximum flow of 1000. And notice that this is a semi-log plot, so there is a nonlinearity to the load versus flow rate. Now, if you're defining a rating curve at a diversion location, which means flow from the main channel could be exiting the main channel either through a junction or through a lateral structure, there's a checkbox right here that says define diversion load. So if you click that, what it does is it opens up this lower table. And what we need to do here, it shows the same number of columns that's defined up at the top, in my case, 2 columns. And then what we need to do for the flow is define a negative flow rate because this represents the amount of flow leaving the main channel. So if I said negative 100, yeah, this was happening to me when I was prepping for the lesson. I'm not able to actually type values in here, even though I am starting off with a negative character and I have my num locks on. Okay, yeah, it seems to be locked for me, but I did have success copying. So let me just try doing a copy paste. Okay, so that works, but I really do need to have negative flows up here in the top row. What may also be the problem for me is I don't actually have a lateral structure or any way for water to be diverted out of this River Station 5000. So anyway, I'll look into that later. But as a consolation, I'll bring up the user's manual and show you what the screenshot looks like. This page right here is the link I'll leave in the description of the video. But what we're covering in this video will be all of the sub pages as well, from add sediment boundary location down to junction and flow split. So rating curve is the page that I'm currently talking about. Okay, and once that page loads, let me go ahead and go full screen. Okay, just kidding. It was actually in the diversion load link that I had to click on to get this image that I want to show you here. So here's the top table with the positive flow values in that first row. And then if you click on the checkbox, you define data here for negative flow rates, negative 90,000, negative 19,200, negative 15,300, and so on. And then the values that you want to type in for each grain size class for this lower table are not loads like they were in the upper table. What they are they're going to be the percentage of that grain size class that gets diverted. So for instance, a 1 value here, which you see in some of these smaller grain size classes, means that it's going to divert the total grain size class mass. But for values less than 1 or left blank, which represents 0, 0.2, that's 20%. That means it'll divert 20% of the total grain size mass class for that particular flow for the particular grain size class. Here it says HEC RAS uses this rating curve in the lateral flow if the lateral flows are negative, hence diversion out of the main channel. All right, let's go back to our table here. And that is all I have to say about the rating curve boundary condition for sediment data. So I'll click OK. Now we have that data saved here. If we ever want to go back to it, we can just double click or click on rating curve. But let's go ahead and define the next boundary condition, and that is sediment load series. Sediment load series adds sediment to a specific location or boundary location in the model, and it's independent of flow rate. As you can see, there's two different ways to add the data, either in the table manually, enter table, or read in from a DSS file. These two radio buttons here also have tabs down here, so manual entry versus DSS. Let's talk about the manual entry first. So what we want to do for manual entry is to specify either simulation start time, which coincides with the start time of the actual compute routine, or fixed start time, in which case we'd have to specify the start date and start time. All right, down below here, we have two tables. On the left here, we represent the sediment and load, and then also the duration of that sediment load. So right now, the starting date time is what I'm using, the simulation time, January 1, 2020. So that's right there. And then what I would do here is I just start typing in numbers. So if I have the daily sediment load, I could just type in 24 for the hours. And you notice that the elapsed time is calculating 24, 48, and 72. And now I just typed in some numbers right here. So this is the sediment load at River Station 5000 per day. So every 24 hours. This is the time series data, you can think of it. And it is independent of flow. Up above, I've got some buttons that you may have seen from other HEC RAS interfaces before. Number of ordinances, if I wanted to change it from 100 to something else. That's the number of rows in this table, if I need more, for instance. You can obviously have more but not use them all. There's no problem with that. Interpolate values, so that works as before. If I had flow data down here and it was 9,000, I can go ahead and click here, interpolate, and it gives me the, looks like a linear interpolation on that sediment load value. And then we can also delete rows and insert rows. Okay, over on the right here, we have the gradation rating curve. So this is the gradation of the sediment load that we're entering for this boundary location. As before, we can control the number of columns in this table. And I'll just stick with 2 again. The label is number of flow load points, but it's really not related to flow. It's just related to the load in tons per day here. So this is tons, and then we do happen to be using 24 hours, so that's makes it convenient here. So what we want to do again is create a minimum bound and then a maximum bound. And then if we use more than 2 columns or 2 sets, we can add a number of intermediate data points for separate columns as well. But for this data, I just need to have a value less than 4154 and a value at 9,000 or more. So let's just go ahead and say 1,000 and 10,000. Okay, now let me go ahead and add some data here to the table. All right, so I've populated this table, and what you're seeing here is the grain size distribution by grain class for that specific load per day or tons per day. The other way to enter data for sediment load is to click on the Insert Data from DSS, this tab right here. What you're going to do is specify the grain class and then click on the DSS file and path button. And as before with selecting DSS data, you're going to go ahead and select the file and then check the checkbox to see the paths inside that file. I don't have an example of this, so I'm just going to use this DSS file, but you can remove the file or select the Find File button right there. Select the file, and now in this table below, we see all the paths that are associated with this DSS file. So we go ahead and select the path that is appropriate to define the sediment load for that specified grain size class, and then click OK. So once we have that selected, we'll pretend this is for clay. We'll go ahead and select clay. That's the smallest size. I'll click this button here to add DSS path to the list. So we'd go ahead and do that for all the grain size classes that we have data for, and then that would be how we define that data. We can also remove classes by selecting it and then clicking remove. Oops, there we go. Okay, that's gone. The user's manual does have a good discussion on this. See, here it is, defining a sediment time series manual and DSS. If you scroll down to the bottom of this page where it talks about the DSS entry, here it is. This image right here, I think is pretty good. It talks about parts A, B, C, D, E, and F that are sort of like the metadata for the series of the path that is a part of the DSS file. So what you're going to do is for part A, that's the river project. For part B, that's the location. Those two parts are really more informational. Part C, sediment, in all caps, that's important. And then the date time will be your part D. The time step will be whatever your time step is. 1 day is pretty typical. And then for part F, this is also a pretty a smart way of doing it, I think, is to specify the grain size class by number underscore and then label 10 underscore VCS. I'm not sure which that is. It's probably a sand. Oh, very coarse sand is my guess. Your units are most likely going to be tons or some other unit of mass. And then the type, you're going to want to use period cumulative most likely. That's what they did here. So I think that's probably the way to go. So anyway, if you're not familiar with DSS View, you can go ahead and watch my DSS View playlist. But what you'd end up doing to define that is create a DSS file. Let me just create a file real quick. I'll just put it on my desktop. Okay, thank you. You go to data entry, manual time series, and this right here is the same interface that we saw in that screenshot right here. So what it's doing is it's creating or editing an existing time series data set that represents sediment. So your part C here would be sediment. Part E here is the time step. Part D would be auto-populated based on the start date time. And then part F would be, like I said, it's optional, but it makes a lot of sense to specify the grain size class by number in abbreviation right here. Okay, getting off on a little bit of a tangent, let's go back and talk about the other boundary conditions. Okay, so we talked about entering data and DSS data. We're done with that. That was all part of the sediment load time series option. The last three are really quick. It's equilibrium load, capacity ratio. These two kind of work together. So if I select on, let's go ahead and pick 3000 now. Oh, okay. I don't have equilibrium load available to me at 3000. Let's stick with 5000 then. Equilibrium load, boom. There's no data to fill out. It calculates the sediment load from the bed gradation and transport data. This first tab here in the dialog box for initial conditions requires us to specify a bed gradation, which I do not have defined yet, but you can do that here. Again, that's all in lesson 53, but we can basically let the boundary conditions just use the gradation that's already defined in the initial conditions. The next boundary condition over is capacity ratio. So that basically takes the equilibrium load and then multiplies it by a factor. So if you just use 1, which is the default, that'd be the same thing as the equilibrium load, I presume. But if it's maybe 50%, you'd do a 0.5. If it's maybe 80%, you'd say a 0.8 or something like that. And then the last option here for boundary condition at a cross section is clear water, no sediment. Again, there's no metadata to fill out. This is a simple way to define a no sediment boundary, which would be used to model no sediment. For instance, maybe you have a high trap efficiency dam or other boundary that stops sediment. All right, the last part of this lesson, I want to talk about the different boundary conditions for sediment related to a junction. So if we click on junction, now we have these bottom options available to us. We'll start with this one, flow weighted sediment split. So if you click on that, it automatically populates the table. There's no extra user input data required. And what this does is it splits the sediment mass proportional to the flow. HEC RAS knows what the flow split is at the junction. It also knows what the sediment flow is based on that flow split. I should probably also mention that these junctions are only for the flow split junctions, not dendritic junctions. If you have a junction where multiple rivers combine together at a single confluence, hence dendritic, then what you're going to have for sediment load is just going to be the sum of the sediment from the two rivers that flow into that junction. So you don't even have the option to add any dendritic junctions. But this is a flow split junction, so that's what we're talking about here. The next one over is potential weighted sediment split. This boundary condition weights the sediment based on the flow rate squared. So for this previous example with weighted based on the flow rate, that's a linear relationship between the flow rate and the sediment load. But for potential weighted split, the sediment load is a function of the flow rate squared. So if, for instance, we had an equal flow rate through both downstream reaches, then we'd have an equal load. But if we said that this river A had twice as much flow than the river B, then that means 80% would be flowing down river A and only 20% would be flowing down river B. In the junction and flow split page of the user's manual or the 1D sediment transport document here online, there's a graphic here that shows the flow weighted sediment split, which is the linear. This is the first option. The second option that I'm talking about uses this squared equation where the sediment here is a function of the flow rate squared. So these are different numbers than I gave in my example, but for instance, if the flow splits 4 to 1, like 80 CFS to 20 CFS, you can do the math and then you'd have like 64 parts soil going through the main flow and then just 4, I believe, or it comes out to 6% of the sediment load going through that smaller flow rate. So there's this equation right here for potential weighted. Okay, so if I click on junction again, the third one is GC threshold split. This is flow weight rated sediment split at a junction, but only for grain classes finer than the selected threshold. So if you click on that, oh boy. Okay, my HEC RAS crashed when I clicked on that. So I need to add my junction back in here. And there's the junction and what it did. Okay, so now it works. Great. Great software. So anyway, the what you want to do is select the grain size and whatever grain size you select here and click OK. Then what's going to happen is HEC RAS will not divert any of the sediment larger than this selected grain size through the smaller flow. So the smaller flow would be the tributary. In my case, it would be this river B that flows off to the side here. Also, the cancel button doesn't work. So just so you know. All right, anyway, the last one here is sediment split by grain class. And this looks a lot like the very first option of rating curve. This option works like the diversion rating curve boundary condition. If the div load row is left blank, that's this one right here, then HEC RAS will use a standard flow weighted split, which is what we had for the first button. Okay, so what we want to do is select the flow rate for all the columns. That flow rate should subsume or encompass the entire range of flow rates that we would see through that diversion. And I've added in some data now. So for instance, 0.5 here for very fine sand. This will divert 50% of the very fine sand through the diversion and then leave the remaining 50% flowing downstream. There, I made the plot a little bit bigger. So 50% and 50%. This 20 right here for div load, diversion load, refers to the total tons per day of sediment for the sum of all the grain size classes. That would be diverted. If the main channel flow entering the junction is 250 CFS. So that's how that works. All right, well, that was it for boundary conditions. What we did was we opened and worked on a sediment file, and then we went to this second tab for boundary conditions, and then talked about the different boundary conditions available for both cross sections as well as junctions in HEC RAS.